Hi, my name is David Van Vranken, and I want to welcome everybody here to our 15th lecture in Chemistry 51C here at UC Irvine during the fall of 2020. Everything's shut down. The campus is, at least for undergraduate instruction, is shut down, so we're doing everything using Zoom. And I think we're finding ways to make it work, even though it's a little bit awkward. I always worry that you as a group are not finding enough ways to connect with other students. That's really going to be the biggest value you get out of an undergraduate education at a major university, is the network of people that you get to know, because those people will help give you buoyancy in your career and as you make a transition beyond UCI. So find ways to connect with people, find ways to connect with me and the TAs, and just keep going. I saw an article about the Food and Drug Administration issuing a warning to some manufacturer of supplementals. The Food and Drug Administration does not allow anybody to make claims about the therapeutic benefits of molecules that have not been proven to be effective against human diseases, which takes years of efforts and clinical trials. So here was an example where the FDA issued a warning letter to some company. They do this all the time, saying, hey, stop claiming that this thing that you're selling here is effective in some way against the coronavirus. So there's plenty of companies that as soon as COVID came out, they realized that they might make some extra money by claiming that it could help knock down coronavirus or COVID or be therapeutic in some way. So when I looked at this, they were talking about some of their products that related to their commercial names. Elixir, salidroside sounds like a chemical name. And some of these things are common. Rosehip, that's a source of vitamin C. Vitamin D3, it's important for bone growth. But there was another, I don't know what it is. It's some sort of a plant or a botanical called ashwaganda. And I'd never heard of that before. So I got interested. What is this ashwaganda that they're selling to people and trying to get them to take some sort of ashwaganda supplement? So when you get onto Google and you type these types of search words, you can come up with a lot of hits, but you don't find anything for ashwaganda and COVID because Google automatically deletes anything where people are trying to make false claims. So I went over to the DuckDuckGo web browser and typed in ashwaganda and COVID and was able to pull up some of the kinds of things that might be appearing in other countries that are not controlled, or on other search engines where they're not being so careful. And you can see all kinds of claims that were being made about ashwaganda and COVID-19. And I'm sure none of these are actually proven in any way to be effective against COVID-19, because if it was some kind of a cure, we'd be using it. So what is this ashwagandha? It's some sort of a plant that, if I understand correctly, is related to Ayurvedic medicine. Maybe I think of the country of India when I hear those types of terms. So ashwagandha is this plant, and I guess maybe it's the root part that they're interested in. They grind it up and make a tea, or grind it up and make pills that people can take. It's more specifically genus and species Withania somnifera. Sounds like it puts you to sleep. Now, what's in there that might have any kind of activity? It looks to me like it contains some sort of steroid molecule. With afferin A has the classical 4-ring steroid system, an A, B, C, D ring, just like you find in testosterone and estrogen and corticosteroids, with some extra stuff on the end. And when I tried to look at these, one of the particular components that seems to be common in there is this molecule with afferin A. None of those molecules have super potent activity, and that's what you're looking for in something that's going to be a promising drug that could be improved upon by synthetic chemists that act as medicinal chemists. I don't see anything in this ashwagandha that looks like it's that there's any evidence that it's going to be powerful against COVID, any more so than just taking extra vitamin C, which boosts your immune system. Who knows how much they're charging for this? Again, there's no substantiation, as usual, for the claims that it's going to treat your COVID infection. So just kind of interesting, though, to find out what kinds of natural products are in these types of supplements, and this idea that people are trying to increase their sales by claiming it's going to cure COVID or help to treat COVID. So let's go ahead and go back to our regular lecture. We are right in the midst of talking about carboxylic acid derivatives. And in our last lecture, we talked about methods for forming amides. I showed you this powerful reagent, DCC, where you just take a carboxylic acid and you take an amide, you mix them together and you add DCC, and suddenly you make an amide out of that. And we also talked about in the last lecture Fischer esterification, where you take a carboxylic acid and an alcohol like methanol or ethanol and a powerful mineral acid like hydrochloric acid or sulfuric acid, and you boil it and you can drive the equilibrium towards making esters. And what I'm showing you now is you can do exactly the same reaction where you take a carboxylic acid derivative, and in this case you use excess water and it drives the reaction back to the carboxylic acid. So you take an ester and you take water under those same Fischer esterification conditions. It could be catalytic HCl here, or catalytic sulfuric acid I'm showing in this case. And just by switching the solvent to water, you can drive esters back to carboxylic acids. Note that there's two products in this reaction. The chemistry cleaves, chemically you're cleaving this carbon-oxygen bond and replacing it with an OH there. So you're going to get methanol as a byproduct. If it was an ethyl ester, you'd get ethanol as a byproduct. This is not a super common set of conditions for hydrolyzing esters, but if you've already taken the time to memorize Fischer esterification, then you can take advantage of the fact that you can just drive the reaction backwards by using excess water. Now the mechanism for this reaction is just like the Fischer esterification. So it starts off by, I don't really want to draw out the whole mechanism for this, but the first intermediate is going to be that you're going to protonate the carbonyl group, just like we did with the Fischer esterification. And that makes it possible for weak nucleophiles like water, right? Oxygen's a weak nucleophile. So under these conditions, even water can act as a nucleophile, just like in Fischer esterification. Even methanol can react with a carboxylic acid if you protonate the carbonyl. So I expect you to know the mechanism. It's a 6-step mechanism. It's exactly the same intermediates as you get in, as you have going on in Fischer esterification. So go ahead and finish up the rest of this mechanism and be familiar with it. Again, I expect you to know the Fischer esterification mechanism, and therefore I expect you to know the mechanism for this, for the opposite, for the reverse reaction for Fischer esterification, where you protonate the carbonyl, alcohol adds, you do some proton transfers, and then you boot out the leaving group. All right, now how do people typically hydrolyze esters? We don't use acid, it's not the common way, and boil things in acid, just because you have to boil things, and it's easier to run these reactions at room temperature. So if you're an organic chemist like me, or maybe a soap maker, the way you cleave esters is you use hydroxide anion as a nucleophile. And these are the most common conditions for hydrolyzing esters. And I want to focus your attention on the fact that this occurs at room temperature spontaneously. If you have ever taken sodium hydroxide solution and felt and rubbed it between your fingers, it's not going to corrode your fingers instantly. Your fingers will feel slippery, and that's because you're turning your skin cells into soap as the sodium hydroxide is exposed to that. So anytime you take lipids or fats, lipids and fats are composed of esters, and you treat them with sodium hydroxide, you're simply converting those, you're hydrolyzing those, just one moment here. You're hydrolyzing those at room temperature. So here's what you get when you cleave that bond. Let me go ahead and note which bond is getting cleaved here. You're cleaving this bond, and the product of the reaction may not be so obvious to you. Let's go ahead and write out the products of this reaction. I think just like acid, the cleavage under acidic conditions, your byproduct for this is the alcohol. So in this case, if it's a propanoate ester made out of propanol, an ester made out of propanol, you'll get one propanol as the one of the two products in this reaction. The other product of the reaction, the carboxylic acid derivative, you're going to end up getting as the anion. I'm going to draw it as the charge separated species. but you could also draw a full covalent bond between the sodium and the oxygen. And let me make sure I draw the right number of carbons in this chain here. I think that matches the right number of carbons in that chain. So the product of this reaction, it is so fast and so spontaneous. You can't stop this from happening. Sodium hydroxide and an ester is going to cleave to give you this sodium carboxylate salt. You'll cleave the oxygen. Now, usually, if you're making this is the chemical structure of soap. Ivory soap usually has about 18 carbons in there. Let me just go ahead and identify this molecule. This is kind of like soap, but soap usually has 18 carbons, 16 carbons long. So I didn't draw the whole substrate because I didn't feel like drawing all those carbons. But that's the chemical structure of soap. It's a sodium carboxylate salt. Now, synthetic organic chemists like to isolate neutral molecules because we can extract them into organic solvents and then evaporate off the solvent. And so how do you get the carboxylic acid using this process? And because this is the way you make soap, because this is the way people made soap 200 years ago, 300 years ago, 400 years ago, I don't know how old soap making is, we call this saponification, which means soap making. So this phrase of using hydroxide anion to cleave esters without boiling it, just at room temperature, we call that saponification. But it's hydroxide anion cleaving an ester. So how do we do this normally so we get the neutral carboxylic acid? We have to do it in 2 steps, which may seem like more work to you, but it's not really more work when you're in the lab. So step 1 here is going to be the saponification conditions. Watch how easy this is. I'm just going to write step 1. Actually, I could use either the small Roman numerals or Arabic numerals, doesn't matter. I'm going to write sodium hydroxide. Could you do it with potassium hydroxide? Sure, you could do it with. It's just that sodium hydroxide is cheaper, and there's no advantage to using potassium hydroxide. You can buy sodium hydroxide in the grocery store. They sell it as lye, L-Y-E, as a drain cleaner because it cleaves the grease clogs that clog up sinks through exactly this reaction process. And then step 2, if you want to protonate a carboxylate anion, how do we do this? You can't just use water. Water's not acidic enough to protonate a carboxylate anion. We have to literally have to use HCl to do this. A lot of times, we're not yet trying to use the HCl to add HCl across the double bond. We're not trying to use the HCl to do some SN2 reaction. We just want to protonate the carboxylic acid. And so since that's the whole purpose of the acid, you need something strong, more acidic than water. I like to write the word work up there to make it clear. We're not trying to do extra chemistry with the H or the chloride anion. So I think in the book there's an extra section in there that talks about lipid hydrolysis, taking lipids and cleaving those ester bonds in lipid molecules in order to, let me go ahead and draw out a typical lipid structure just so it's clear. Like if I keep using the word lipid, what's a lipid? It's a triester molecule that looks like this, and you've got this long chain. Here's another ester, it's a long chain. Here's another ester, it's usually some sort of a phosphate dianion ester attached to something with a positive charge, so we'll just put a circle. You don't need to memorize that structure, but you might have seen it in a biochemistry class, and sodium hydroxide will cleave those ester bonds at room temperature so easily, and that's one of the ways for making soap. And fat just has 3 esters instead of 2. So, in the lab, I use the sodium hydroxide method for cleaving esters, and I do an acid workup. But for you, if you wanted to do this just acid and water and boil it, okay, that's might be easier for you to write it as a 1-step method on the exam or on a problem set that we work. So, all good. Okay, esters. Boy, sodium hydroxide, so easy and so facile to cleave esters with sodium hydroxide. But what about amides? Nothing's easy. Nothing's easy with amides. You know, human DNA and nucleic acids are made with phosphate esters. They are hard to cleave chemically. And that's why your DNA is made out of phosphate diesters. Proteins are not, it's not like proteins are your genetic material. They're pretty stable, but they're still hard to cleave. They're not as hard to cleave as a phosphate ester backbone of DNA using chemical cleavage, but they're still pretty hard to cleave. So pretty smart that the proteins in your body are connected together through amide bonds, because it takes some serious conditions to cleave an amide. I'm going to show you two sets of conditions, and they both involve using concentrated reagents and boiling the heck out of an amide to try to get it to cleave. So here's the two conditions that I'm going to give you. One is concentrated base, and the other is concentrated acid in water and boiling. And those are the only two conditions, concentrated base or concentrated acid. So if you just use 1 molar, so normal is the same as molar. You may be confused why I'm using the normal. I don't know why. Let me change that to molar. Some people get confused. It matters if for a base like calcium hydroxide that has 2 hydroxides. So, but for here, I'm just going to change that to molars because there's no reason to make a distinction between molarity and normality. So 4 molar sodium hydroxide, man, that is concentrated sodium hydroxide. It'll slowly etch your glassware if you leave it sitting for a year, those types of concentrated solutions. So when you cleave an amide under those conditions, here's the bond we're going to cleave. It's this bond right here, and it's this bond over here. That's the bond we're cleaving with these conditions. And so let's go ahead and draw out the products of that reaction. You'd think the products would be a carboxylic acid and an amine, but be careful with that. Let me go ahead and first draw out the amine here, because you certainly get an amine under these basic conditions. But you can't have a carboxylic acid in 4 molar sodium hydroxide. It would get deprotonated. So the product you get out of this reaction, the two products you get are the sodium carboxylate salt and the amine. You can't deprotonate the amine with sodium hydroxide. We'll talk about that a little bit more in the next chapter. I don't know why I circled those charges, just because they look nicer there. So the product, when you use base, there's no way to get 2 neutral products. So if you want the carboxylic acid, you'd have to then treat this with an aqueous HCl workup in order to protonate the carboxylic acid and make it neutral. So what do you do here with the acidic conditions? Well, with the acidic conditions, they directly give you the carboxylic acid. You know, you might be saying, oh, don't you protonate the carbonyl? Under acidic conditions, only a tiny amount of the carbonyl is protonated at any point in time. You know, over 99% of the 99.9% of the carbonyls are neutral, just a tiny fraction. So the product is the neutral carboxylic acid, but you don't get the neutral amine when you're boiling things in 6 molar hydrochloric acid, right? There's no amine sitting around. It's all protonated. So I'm going to draw that as the ammonium salt. And the counterion in this case is chloride, because it uses, these conditions use hydrochloric acid. You've got to heat this. If you were doing, I think probably on the sapling system, we just write a symbol delta there. So maybe I'll just indicate that here. I'm just telling you the temperature and the time to try to convey how aggressive these chemical conditions are. So if you just, I think on sapling, it just has maybe delta or heat, and it doesn't tell you 10 hours, you know, for if you're just doing homework or a problem set, do you care that you have to boil it overnight? No, but I do when I'm in the lab. It matters to me because I have to plan out my day and my evening, that all lab workers do. So what's going on under these conditions? Let me go ahead and draw mechanistically what's happening. Right? It's so hard to add to an amide that under the conditions over here, and I'll switch back to my black pen for high contrast. You know, the reason why this reaction works, you still have to heat it, is you've got a powerful nucleophile. And it's still not a very fast reaction. So under the basic conditions with the sodium hydroxide, you've got a powerful nucleophile, and that's what makes that work. It doesn't work at room temperature, but if you heat it, it will work. When we come back over to the acidic conditions, why is it that you can get an amide to cleave? Amides are so hard to cleave. Well, they cleave not because you have a powerful nucleophile. Under the acidic conditions, you have a lame nucleophile, water. There's no significant amounts of hydroxide anion when you've got 6 molar hydrochloric acid. So in hydrochloric acid, the main nucleophile is water, but water is not going to easily attack the carbonyl. It would just bounce right off. So you have to protonate that. That's the goal of the acidic conditions. When you do the 6 molar HCl, you got lots of water. It's a lame nucleophile, but there you're just taking advantage of the fact that you've got enough of the protonated amide, small amounts of the protonated amide in there, that it can be attacked by water. So I'm not going to draw out the whole mechanism for you. You don't need to worry about that. There's an extra section in the textbook that talks about beta-lactams. A lactam is a cyclic amide. Let me go ahead and draw out a lactam for you. Here's a lactam. Just any cyclic amide is called a lactam. That's called a lactam. Beta-lactams are four-membered rings because the nitrogen is on the beta carbon. So a beta-lactam, why would they have an entire section on this? And that's because there's an entire class of antibiotic drugs that have these four-membered ring lactams there. This is a beta-lactam. And so I think there are hundreds of beta-lactam antibiotics. If you've got a bacterial infection that's either systemic or local, you'll often be prescribed beta-lactam drugs to kill bacterial infections. And they have this very strained four-membered ring with a, somewhere on the order of 26 kcals per mole of ring strain. And those will cleave rather easily. In fact, they chemically react with one of the key enzymes that you find in sort of bacteria that build the cell walls. And so it's kind of fun reading. I'm not going to ask you any questions about beta-lactam antibiotics on our exam. But if you're interested in medical school or dental school or any sort of health-related profession, it's worth knowing the structure of beta-lactams. They're just four-membered ring cyclic amides. Now the book has this kind of study guide for you. I'm repeating it here. There's no new information in this chart here. But this chart that comes from table in the second edition of the Gorzynski-Smith textbook, this chart that comes from table 22.5 helps you to organize all the reactions that you've learned in this chapter. So we've told you that acid chlorides can be used to synthesize carboxylic anhydrides. Acid chlorides can be used to synthesize carboxylic acids, though nobody would do that. But it's a side reaction. Nobody would do that because you always make acid chlorides from carboxylic acids. You can use acid chlorides to make esters. You can use acid chlorides to make amides. I expect you to know those reactions. They also tell you that you can use anhydrides to make carboxylic acids, but nobody would do that. Nobody would purposely do that. It's more useful to take anhydrides and make esters or amides. Amides are far more common for that reaction. You can take carboxylic acids and use them to make acid chlorides, thionyl chloride and heat, remember? You could use carboxylic acids to make anhydrides. We didn't talk about that much. You have to deprotonate it first and react it with an acid chloride. And you can use them to make esters with Fischer esterification. And if you mix carboxylic acids with amines and use DCC, I expect you to know that you can make an amide bond pretty easily. So there's all these reactions in here. You can't, so what can you do with an ester? Well, you can hydrolyze it to a carboxylic acid, and the book slightly mentions that you can do something called aminolysis to cleave, but that's not that common, so I didn't spend time. But you should go back and review that section. And then finally, what can you do with an amide? Very little. You can cleave it to make a carboxylic acid. There's other reactions you can do with these, with Grignard reagents and lithium aluminum hydride, but just converting one carboxylic acid derivative into another. Here's a table that summarizes all the stuff you should know that you should have learned in this chapter. It'll just help you organize. Did you actually learn all these transformations, and can you remember the conditions? There's some extra sections in this chapter. There's something on natural and synthetic fibers, and they'll tell you about the structure of nylon, which is just an amide, a molecule with two carboxylic acids on each end, making amides with another type of molecule that has amines on both ends, and then forms a long polymer. And there's other polymers that are composed of amides. And then they'll talk about making some other types of carboxylic acid derivatives. Biological acylation reactions, you guys, if you've taken a biochemistry class, you've heard of acetyl-CoA, which is a thiol ester. Maybe it'll tell you about the ribosomal synthesis of peptides and proteins, it's all amide bonds, amide bond, amide bond, amide bond, and oligomerizing those. So I'm not going to ask you to memorize the things in those sections, and then, I mean, that might be great for a biology class, but I typically ask you about chemical transformations and mechanisms and things like that. But it's fun reading. Okay, in the 5th edition of the Gorzynski-Smith textbook, they have this section on nitriles, and it feels to me like maybe it was moved around somewhere different in the 6th edition of the textbook. I can't remember exactly where that was positioned, but this is in in most textbooks, nitrile chemistry gets put in the same chapter as carboxylic acid chemistry. And of course, a nitrile is a triple bond, not a double bond. So, but it reacts, the CN triple bond is reactive on that carbon in the same way that a carbonyl carbon is reactive. So one reaction that we've already told you about back in the previous chapter is how to hydrolyze cyanohydrins, the nitrile group of a cyanohydrin. Let me go ahead and remind you of how do you make cyanohydrins. So if I wanted to make a cyanohydrin, you add HCN, but you can't buy HCN. You make it in the laboratory by mixing sodium cyanide powder with hydrochloric acid. And that will convert aldehydes and ketones into a type of functional group called a cyanohydrin. You've got an OH right next to a CN. That's a cyanohydrin. And I told you back then when we first learned about this, this is the first reaction from the last chapter, that, oh, you can hydrolyze cyano groups to carboxylic acids. And that's true for all cyano groups. When you treat them with harsh conditions, the same one that cleave amides, 6 molar hydrochloric acid, and then water and heat. I told you, 100 degrees, 10 hours. I'm just going to write a delta symbol under here. But it's like you got to boil the heck out of it overnight and come back the next day. And then your nitrile group will be gone. You might be wondering, what happened to that nitrogen atom? Well, it turned into ammonium chloride, but we don't write that. It's got no carbon atoms in it. But if you're really fascinated into about what happened with that, what happened to that nitrogen atom, it turned into ammonium chloride and gets washed away and thrown out with the aqueous layers when you do the workup for this reaction. Okay, so those conditions, it doesn't matter how you make a nitrile. So let me just remind you, you've made nitriles in other ways in previous chapters. If we go back to the chapter on SN2 reactions of alkyl halides, you should have learned that you can take sodium cyanide and use that for SN2 reactions. Cyanide's a nucleophile. I'll just write sodium, and there's a lone pair on the carbon that will attack and do SN2 reactions. We'll teach you another way to make aryl nitriles, where the nitrile is directly attached to the benzene ring when we get to chapter 25. But again, it doesn't matter where you get your nitrile from. You could buy this if you wanted. But if you treat it with these conditions, 6 molar hydrochloric acid, concentrated, I should put a space. Normally in science, we put a space between number and units, 6 molar, 10 inches, 5 centimeter. Normally, I'm sorry I didn't put a space between the 6 and the molar. Hydrochloric acid, and then water. And then boil it at 100 degrees overnight and come back. And you'll cleave that nitrile, you'll hydrolyze that nitrile group all the way to a carboxylic acid. And now, of course, you could use this to make acid chlorides and do Friedel-Crafts reactions, or make esters out of that, or do a DCC coupling with an amine to make an amide. Wow, so pretty cool that you can make nitriles and convert them into carboxylic acids. If I showed you the arrow pushing mechanism, it's at least 12 steps long, and I'm not going to ask you a 12-step mechanism on any of our sapling homeworks or any of our exams, so I just don't have the energy to go through that with you right now. So, and I'm not going to ask about that, and I don't think anywhere in the book it asks you to memorize that mechanism. So let's just set that aside, but it's very cool. It's the same as the hydrolysis mechanism for an amide. Okay, what else can you do with nitriles? I thought we had covered this before, but maybe we hadn't covered this in a previous part of this section. You take a nitrile and you treat it with DIBAL-H, and it's just like taking an ester and treating it with DIBAL-H. You probably don't even remember because we didn't use this DIBAL-H reaction a lot, but it's actually used quite frequently. The reaction of esters with DIBAL-H. DIBAL-H converts esters into aldehydes, and it does the same thing with nitriles. There we go. You can't tell here, but it adds a hydrido group onto the nitrile, and you get an imine that hydrolyzes during the workup. So So if you, later in chapter 25, I can't resist just telling you, in chapter 25, we're going to tell you how to make this bond. It's a super secret. I'm not going to tell you what that secret is. Sometimes I can't resist telling you. But then you can hydrolyze it to an aldehyde using DIBAL-H and water, just like we did with esters later. The other thing you can do with lithium aluminum hydride, and I apologize because I wonder if I can erase this because that L should not be capital L. That's kind of bugging me here. Let me see if I can make that look more like a, there we go. That's kind of like a lowercase L. Lithium aluminum hydride. We'll add 2 hydrido groups into that nitrile. Just like an ester, you add 2 hydrido groups. But in this case, you get the same product as reducing an amide, you get a primary amine. Let me go ahead and draw out that product here. Here's the product for hydrolysis, or sorry, reduction of that amide. It's going to be now singly bonded, and we've added 2 H's on there. Let me go ahead and draw them. Maybe I can draw them in light gray just so we don't spoil our nice looking primary amine. There's the H's. We normally don't draw those H's. You're expected to be able to see that they're there because you've drawn so many organic molecules. But again, anytime you put a nitrile in a molecule, you can use this lithium aluminum hydride reaction to convert that into a primary methylamino group. So you've got a CH2 right next to an NH2. Anytime I see some sort of an R group, let me switch back to the black here. Anytime I see a molecule that has a CH2 next to an NH2, I'm thinking, oh, I could have hydrolyzed a nitrile to get that group, right? You ought to be thinking that I could have made that from reduction of a nitrile. So you need to remember that functional group transformation. I'm sure we have it on the problem sets. Who knows? It may end up on an exam. I won't know that till I'm sitting and writing the exams which of the 1,000 reactions you've learned I'm going to put on there. Okay, so what's another reaction you can do with nitriles that's kind of like a reaction that you would have done with an ester, but a little bit different? If you have a nitrile, we can add 1 equivalent and stop of a Grignard reagent or an alkyl lithium reagent, and you can't stop with an ester. If you take an ester and add Grignard reagent, you can't stop it from adding twice. So you might as well add 2 equivalents. But here, you only add 1 equivalent. The product of the reaction, in this case, just adds 1 ethyl group. There we go. That's kind of useful. You can't do that with an ester. You can't stop at the ketone because the Grignard would react with the ketone faster than it reacts with the ester. So what's going on here in this reaction? Let's go ahead and draw out how to think about what's going on. You know, cyano groups are kind of polarized. The nitrogen's electronegative, and so it wants all the electrons. It makes it easy to attack that nitrile carbon. Let me go ahead and draw out our Grignard reagent. And it would be the same idea if it was an alkyl lithium reagent. So we've got this nucleophilic bond here between the ethyl and the magnesium, and that adds in. Well, let me switch over to a red pen for that. And it adds in. Push the electrons up to nitrogen, which is electronegative, kind of like a carbonyl. Should look very reminiscent of carbonyl chemistry. And the intermediate that we're going to get, everything is probably fine up until this point, is going to freak you out. It's like, what is that thing? I've never seen anything like that before. Okay, I realize that, but it's just going to sit there. It'll associate with the bromomagnesium salt. It'll actually end up forming a bond, but it doesn't matter. That gets hydrolyzed during the workup. When you treat this with water, you just wash it with water, and imines are pretty easy to hydrolyze. And you just do an H2O workup on that, and that will give you the ketone. So if you're freaked out by this very weird looking imine anion, don't worry about it. It's not. If you don't want to, don't worry about the fact that that's there. I think this is one of the industrial syntheses for a very happy molecule, Wellbutrin. I think you use that for depression, or maybe if you're even feeling good and you take some, you'd probably feel even better. It looks a little bit to me like a methamphetamine derivative. It's a derivative, I think it's a derivative of this Middle Eastern plant herb they chew called cat, Q-A-T, that you use to get kind of high. And I guess Glaxo Wellcome must have figured they could put a chlorine on there and make a slightly bigger alkyl group. And that's, I guess it's better than chewing cat leaves. Okay, that's all we have for today. We just finished chapter 22, and chapter 22 has so many reactions in there. Let me just walk us back here to this chart here. We've taught you so many reactions in chapter 22, and this is the end of the material for exam 2, which is going to be next Friday. Next Friday, we're going to have an exam which is going to cover chapter 20, which is adding every type of hydride reagent and Grignard reagent alkylithium to carbonyl groups. So Grignard reagents, alkylithiums, lithium aluminum hydride, DIBAL-H, cuprates to enones. There's so much in chapter 20. We're now doing a bunch of carbonyl chemistry. Chapter 21. Sorry, chapter 20 was all that stuff. Chapter 21 is aldehydes and ketones, making imines, making acetals, making cyanohydrins, and then they threw in Wittig reactions, which didn't really seem to fit in there. I guess they didn't have anywhere else to put that. And now chapter 22, look at all the transformations, the functional group transformations you have to know here. In chapter 22, all the things you can do with acid chlorides, all the things you can do with anhydrides, all the things you can do with esters, and carboxylic acids and amides. And you need to know these transformations. You need to practice the transformations. You need to practice doing multi-step syntheses with the transformation so you know how to work the reactions backwards and forwards. In addition to these, we've got these extra reactions of carboxylic acid functional groups. So you've got a lot on your plate in order to get ready for our exam next Friday. Go practice these reactions. When you're done working our online homework, then go to the textbook and work those reactions, because I'm going to try to give you reactions you have never seen before. That's the only way I can test whether you've really mastered the tools of organic chemistry, mechanistic tools and synthetic tools. So you guys stay safe and stay focused on our class here. I know you've got other classes, but invest in the material. Thanks again for coming to my lecture today, and I will see you guys on Monday.